Hi, welcome to another IGCSE physics video. This is section 1.9, which is about law of conservation of momentum. This is part 2 of section 1.9. There is a link to part 1 in the description if you haven't learned about momentum. In this video we will learn about the law of conservation of momentum, and we will also learn about the applications of the law of conservation of momentum in different types of collisions. So let's begin with talking about the conservation of momentum. The law of conservation of momentum says that the total momentum of an isolated system is always constant. So in any scenario or activity that involves collision of two or more objects that have some momentum, the momentum is never created or destroyed, but it is always conserved. And momentum is only transferable from one object to another. It cannot be destroyed, it can never be created, but it's always conserved. So let's draw an application of what these 3 points mean to get a better understanding of the law of conservation of momentum. So let's say that you were playing on a pool table and you were striking a billiard ball. Let's say that was a black 8 ball, and you strike the cue ball towards it. We know that this cue ball would have some momentum as it had some mass and it had some motion. And let's say that in this scenario, when we strike this cue ball, we have no friction on this pool table. And let's say that as the ball travels, there's also no air that is hitting the ball to slow it down. So there's no air resistance or an external force like gravity which would affect the momentum of the ball. So let's say that you strike this cue ball which has a mass of 1 kilogram and a velocity of 1 meters per second in this direction. Then we know that the momentum of this object would be the mass times the velocity of the cue ball, which would be 1 kilogram times 1 meter per second, giving us 1 kilogram meter per second. So that's the momentum of the cue ball. We know that this black ball originally has no momentum as it has no velocity. And so when the cue ball hits that black ball, the black ball will travel at a certain velocity as the momentum from the cue ball will be transferred to the black ball. And the black ball will gain a momentum of 1 kilogram meters per second as all the momentum will be transferred from the cue ball to the black ball, and it will put it inside the hole. And so we know that the initial momentum of the system was 1 kilogram times meters per second of the original cue ball plus the momentum of the black ball, but that momentum was 0. And in this case, when we hit the ball, all the momentum from the cue ball was transferred to the black ball, making the final momentum of the system equal 1 kilogram times meters per second. So we can see in this case that the total momentum of the system before the collision and after the collision is the same. The momentum has been conserved and there's no change in the overall momentum of the system, even though the momentum of the balls changed as the cue ball went from 1 kilogram times meters per second to 0 kilograms times meters per second as it was stationary and it had no momentum, while the black ball gained a momentum from 0 kilograms meters per second to 1 kilogram meters per second. We can see that none of the momentum has been destroyed or created, except all the momentum from the cue ball was transferred to the black ball. So by the law of conservation of momentum, we know that the initial momentum would equal the final momentum. So we know that the momentum of the initial system is given by the mass of the first ball times the velocity of the first ball in its initial state, plus the momentum which is given by the mass of the second ball times the velocity of the second ball in its initial state, which is the black billiard ball. And all this initial momentum equals to the final momentum, which would be the momentum of the cue ball in this case, which is the mass 1 times the velocity 1 in its final state, plus the momentum of the black billiard ball, which is the second ball, so m2 times the second velocity in its final state. And so in word terms, this means that the momentum of the cue ball in its initial state plus the momentum of the black ball in its initial state equals to the momentum of the cue ball in its final state plus the momentum of the black ball in its final state. And so we know that the momentum of the cue ball in its initial state was 1 kilogram meters per second. And we know that the momentum of the black ball was 0 because it was stationary. So it had a momentum of 0 kilograms times meters per second, which would all equal to the final momentum. And so the final momentum of the cue ball was 0, as when it hit the black billiard ball, it came to a stop. So it had 0 momentum. And finally, the black billiard ball in its final state had a momentum of 1 kilogram times meters per second, as all the momentum from the cue ball in its initial state had been transferred to the momentum of the black ball in its final state. And if we add those two numbers, we get that 1 plus 0 equals to 0 plus 1, giving us 1 equals to 1. And so the momentum of the system is conserved before the collision and after the collision. Now let's solve some word problems of the law of conservation of momentum. A 5 kilogram bowling ball travels at a velocity of 1 meters per second east. So we know that our bowling ball has a mass of 5 kilograms and it also has a velocity of 1 meters per second east. So using the momentum formula, we can find the momentum of this bowling ball in its initial state. So we know that momentum equals to the mass times velocity, and so the momentum of this bowling ball would be 5 kilograms times the velocity, which is 1 meters per second. And let's say that the eastwards direction is positive velocity and the westwards direction equals to the negative velocity. So this will be our standard for this word problem. So the momentum of the bowling ball would be positive 5 kilograms meters per second. And then it says that this bowling ball hits a stationary basketball. So we know that this basketball is stationary, meaning that it has some mass but it has no velocity. Oh, and we're given that it has a mass of 1 kilogram. So we know that the momentum of this basketball would be its mass, which is 1 kilogram, times its velocity, which is 0 because it's stationary. So the momentum would be 0 kilograms times meters per second. And so the momentum of the basketball in its initial state is 0 kilograms meters per second, as it is stationary, and stationary objects have no momentum. Now, after the collision, the bowling ball comes to a stop. So we know that it has no more velocity, therefore it has no momentum. So now the bowling ball would have a momentum of 5 kilograms times the velocity of 0, which would give that the momentum equals to 0 kilograms meters per second for the bowling ball in its final state. So the final momentum of the bowling ball would be 0 kilograms meters per second. And so the momentum would be transferred to the basketball, and the basketball gains some velocity after the collision. So it's asking us, what is the final velocity of the basketball? Well, we know that the momentum of the basketball in its final state would be its mass times the velocity. We know that the mass of the basketball is 1 kilogram, and the velocity is unknown, so we don't know what the velocity is. We know that the formula for the law of conservation of momentum is the first momentum plus the second momentum of the initial system equals to the final momentum of the first ball plus the second ball. So we know that the bowling ball had a momentum of 5 kilograms meters per second, and the basketball had a momentum of 0 kilograms meters per second, as the basketball was stationary. So we can put 0 kilograms meters per second equals to the momentum of the bowling ball in its final state. We know that after the collision, the bowling ball came to a stop, so it has a momentum of 0 kilograms meters per second. And now we know that the final momentum of the basketball would be its mass times its final velocity, and we don't know what the final velocity of the ball is. But we do know what the mass of the basketball is, which is 1 kilogram. So we can put 1 kilogram times V final. So let's simplify this equation. This equals to 5 equals to 0 plus 1 times V final. And we know that this equals to 5 equals to 1 V final. And so the final velocity of the basketball would be 5 meters per second. And the momentum of the final basketball would also be 5 kilograms meters per second, as it has a mass of 1 kilogram times its final velocity 5 meters per second, which gives us 5 kilograms meters per second. And so we can see that the basketball's final momentum would be 5 kilograms meters per second, and 5 plus 0 equals to 0 plus 5, and so the initial momentum is equal to the final momentum, and the momentum has been conserved. This type of collision between the basketball and the bowling ball is an elastic collision, because in elastic collisions the balls did not stick together. There's another type of collision which is an inelastic collision, which I will talk in the next video, which will be part 3 of law of conservation of momentum, which is when the balls do stick together. And this is it for section 1.9 part 1. I hope you found the concepts of the law of conservation of momentum useful, and this basic example of an elastic collision that we just solved. In the next video we will talk about inelastic collisions and more word problems that involve the law of conservation of momentum. Leave a comment in the comment section and provide feedback so I can improve my videos in the future. And I'll see you in the next video. Thanks for watching.